Greetings and welcome to your fascinating lecture on radioactivity. This is presented to you in online lecture format so that those of you who want to get started early on radiation can get started as early as you like. Okay, there are two types of nucleuses, stable and unstable. A stable nucleus is when the strong nuclear force, which is in one hand, balances with the Coulombic repulsion, which is in the other hand. And they both push against each other, equal and opposite, and everyone's happy. The nucleus is stable. But when you have more of one or of the other, the nucleus will radiate in an attempt to bring itself back to stability, and hence you get your radioisotopes. There are two types of isotopes. One is your stable isotope, the other is a radioisotope. Radioisotopes are unstable and they will radiate to achieve a state of stability. Now, in looking at this slide here, and you can load this on the PowerPoint yourself, here we have the number of protons up the side, the number of neutrons up the side here. Here's the atomic number down the bottom here. Now you've got this red line that covers right up here where the number of neutrons equals the number of protons, and that would be a 1:1 relationship, but the line of stability doesn't follow that. It curves up the screen here. And what this says is that as you get further towards high levels of atomic number, you actually require a greater number of neutrons to balance the number of protons. And then everything after about bismuth is radioactive. So the line of stability actually cuts here and stops. Now, your first kind of radiation is alpha decay. Alpha decay ejects a positively charged helium nucleus. So what we're talking about here is 2 protons and 2 neutrons, no electrons. So it's got a charge of +2. The alpha particle will come out at about 5 to 7% the speed of light, which is fast, but not tremendously fast. Now here is how to write a nuclear transmutation reaction. Up here is the mass number, down here is the atomic number. Now it begins as plutonium. Plutonium 240, i.e. 94 protons, and then the neutrons, the difference between 94 and 240, they become 23692 uranium. So the reason is that you've got 4 atomic mass particles here, so 240 goes to 236 as the helium leaves, but your 94 goes to 92 because there's only 2 protons in a helium nucleus. So plutonium transmutes to uranium and an alpha particle and energy. Now you can also represent 42He with the Greek letter alpha, although in stage 2 this is the preference, especially in your exam. Have a look at this slide and have a shot at writing an equation to represent the alpha decay for plutonium 240. Then determine the unknowns for A, B, C and D.